Welcome to this lecture. In this week, we are discussing about convergence of random variables, and we have seen so far three types of modes of convergence, namely convergence in LP, convergence almost surely, and convergence in probability. In the previous two lectures, we have concentrated on convergence in probability, and we have found out that the other two modes, namely convergence in LP and convergence almost surely, imply convergence in probability. In the previous lecture, we have found several reformulations or equivalent conditions of convergence in probability, and we have already used those equivalent statements and seen that these equivalent statements imply or give alternative proofs of results that we have already seen, such as that almost sure convergence implies convergence in probability. In this lecture, we are going to use these reformulations once more to get other interesting results. So, without further delay, let us continue discussing using the slides. So, now we are going to look at these further results, which essentially will give us a better idea about the convergence in probability. In particular, these will also give us a better idea about these comparison type results that we have seen, namely that convergence in LP and almost sure convergence implies convergence in probability. We are going to understand that type of implications a bit more, and the equivalent statements for convergence in probability are going to help us do that. We continue to assume that all the random variables that we are using are defined on the same probability space, which we denote by this symbol. So, this is our probability space. So, this is the first main result of the discussion. So, if x n converges to x in probability, then the statement says there exists a subsequence of this sequence of random variables such that the subsequence converges almost surely to the remote random variable x. Recall from earlier that we have shown that convergence in LP implies such a result, meaning given a sequence of random variables converging in LP, you can extract a further subsequence converging almost surely. So, we could go back to that type of a result, and in fact, we are going to use a similar technique to do this here. Remember, if we can prove the statement that we are going to discuss in this lecture, meaning for convergence in probability, you can extract a subsequence converging almost surely to the limit, then it will also prove the earlier result that convergence in LP you can extract a subsequence which converges in the almost sure sense. So, that result can be proved because convergence in LP implies convergence in probability, and now you can use the new result that we discuss in this lecture to get a alternative proof of the fact for convergence in LP. So, without going into that technicalities, let us focus on the results involving convergence in probability only. But as we shall see, we are going to use similar techniques, but using the equivalent formulations for convergence in probability that we have discussed in the previous lecture. So, let us see. Here we start by assuming that convergence in probability holds. Now, start by looking at these simple triangle inequality, that the distance between two random variables coming from the sequence that can be dominated through these quantities where the distance is taken from the limit random variable. Now, if you choose any epsilon positive, then this difference exceeding epsilon can only happen if at least one of them is greater than epsilon by 2. Note that if both of them are less than epsilon by 2, then by the triangle inequality above we will have that this is less or equals to epsilon, which is not what we want. So, therefore, whenever the distance between nth term and mth term that quantity is exceeding epsilon, we must have one of the quantities exceeding epsilon by 2. So, that is the observation we are using to claim that the left hand side event here is contained in the union of the two events on the right hand side. Therefore, what we can do? We can appeal to the finite additivity of the probability function and write this inequality, that limit as n and m go to infinity, the probability in question, that limit can be dominated from above by the addition of these two limits. Now, here we are using the important observation that even though we are taking n and m simultaneously to infinity, on the right hand side the terms that we have depend either only on n or only on m. So, the first term here depends only on n, the second term here depends only on m. So, even if we write here limit as n m go to infinity, the effect of n does not appear in the second term here. Similarly, the effect of limit in m does not appear on the first term on the right hand side. Now, observe that both the limits on the right hand side, they exist because we have assumed that the random variables converge in probability, and therefore, these limits that appear on the right hand side, they are actually 0. Therefore, combining everything, the left hand side limit, that is a limit of certain non-negative quantities, is less or equal to 0. Therefore, the limit must actually be equal to 0. So, that is what the consolidated statement gives us as soon as we assume that the random variables converge in probability. Now, here you observe that once you have this fact that for every positive epsilon, the probability of this nth term and mth term, that exceeding epsilon, that probability is going to 0, that in effect is going to give us some interesting observations, that these probabilities can be made small by choosing large enough n and m. So, if you choose large enough numbers n and m, what we will have is that we can construct subsequence of the natural numbers, which we denote by capital N sub k, and with the property that this subsequence of course is strictly increasing, and moreover this subsequence is with this specific property that the nth term and mth term will exceed 2 power minus k, that probability is dominated from above by 2 power minus k. Now, for that we will essentially end up with this threshold that depends on k, and since these quantities can be made smaller than let us say 2 power minus k, we can get this threshold n k. Now, once we have obtained n k, then fix that number and start looking for terms afterwards. Then again we will look at the threshold 2 power minus k plus 1, and for that we will look at probability of modulus of x n and x m, that difference exceeds 2 power minus k plus 1. So, that quantity can be made small by choosing large enough n and m, and therefore, we can obtain this n subscript k plus 1. So, that is why we can construct this specific subsequence with these properties. For the simplification of our notation, we write y subscript k for capital X subscript n k. Now, here this new sequence of random variables is actually a subsequence of the original sequence, and for these random variables y k, these things happen. Look at this event that y k plus 1 and y k, the distance between them is at least 2 power minus k. So, that event a k has the property that the probability of that is less or equal to 2 power minus k. So, therefore, if I sum up these probabilities, they must be convergent. Now, we appeal to the Borel-Cantelli lemma first up. This we have discussed in week 1, theorem number 9. Now, as soon as you have probabilities are summable, you will conclude that the lim sup of the events must have 0 probability. Now, use this argument that we have used again in the case for LP convergent sequences that we have used in lemma 1 again of week 1. So, there what we had shown was that as soon as you have obtained this specific set which is of the form lim sup of certain events having probability 0, we can extract the specific subsequence that converges almost surely. That was what we had used in week 1 to extract subsequences from LP convergent sequences, and the subsequences were converging to the limit random variable in the almost sure fashion. Here again we ended up with the same situation where the lim sup of the events has probability 0. We will simply repeat the argument that we had used there, and we will conclude that the random variables that we are using now must converge almost surely to some random variable y. Now, here what we are saying is that as soon as you conclude that the subsequence converges almost surely to some random variable y, then the subsequence must also converge in probability. So, this we have seen earlier that almost sure convergence implies convergence in probability. So, that is what we are using here, but this specific subsequence has the property that it is a subsequence of the original sequence, and we are already given that the original sequence converges in probability. So, therefore, the subsequence must also converge in probability, but to the limit random variable x. So, now we have one specific subsequence which is x n k. Here what we are having is that the limit random variables y and limit random variable x both are limits for convergence in probability for this subsequence. Thus, we conclude that we must have that the two limit random variables x and y must match almost surely. This argument is left as an exercise for you. Please work this out. So, therefore, what we ended up having is that we have constructed explicitly a subsequence of the original sequence such that these converges in the almost sure sense. Therefore, we ended up extracting this specific subsequence. Now, here we have used the Borel-Cantelli lemma argument to obtain or extract this subsequence. Now, we give an alternative proof of the same result, but using the equivalent formulations that we have seen in the previous lecture, namely that given convergence in probability, the expectation of these bounded random variables go to 0. So, here the bounded random variables are modulus of x n minus x divided by 1 plus modulus x n minus x. So, here these expectations are going to 0. So, this is an equivalent formulation of convergence in probability for the sequence x n going to x in probability. Now, here what we are going to do is that from this limit we will extract a subsequence n k of the sequence of natural numbers with again this property that these expectations are smaller than 2 power minus k. So, the way we do that is that for each k look at epsilon equals to 2 power minus k, then since this limit is going to 0, these terms in the sequence must be smaller than 2 power minus k after some threshold, that is what is capital N k, and then after n k we will start looking at a new value of epsilon which is 2 power minus k plus 1, and for that we will end up having the new threshold which is n subscript k plus 1. So, that is how we construct the specific subsequence capital N k. Now, for that subsequence what we ended up having is that the expectation of these random variables is less than 2 power minus k. Now, here we note that as soon as these terms are less than 2 power minus k for all k, then if we look at the expectation of this sum of these random variables, here all these random variables by construction are non-negative, right. So, therefore, we are looking at expectation of sum of certain non-negative random variables, and here we use the monotone convergence theorem to claim that the exchange of limit and expectation works. So, here how do you do this? So, we have discussed this type of an argument earlier. So, the idea is that the infinite sum that we have, they involve positive random variables which are of certain type. Now, if you look at terms up to finitely many entries, so let us say up to m terms. So, that same expression that increases as m goes to infinity. Now, for finitely many terms you can exchange and then you use the monotone convergence theorem to claim that the expectation and the summation, the series of these non-negative random variables can be exchanged. Once you do that, we end up having that here is a series on the right hand side of certain expectations, but these quantities, as we already have obtained, have an upper bound given by 2 power minus k. So, therefore, the series that we have obtained on the right hand side is summable. As a consequence, what do we have is that the term in the left hand side, which is the expectation of this series, that is finite, and hence the random variable in question must be taking finite values almost surely. So, here you note that we are using the general arguments involving measurable functions, that if you have a measurable function whose expectation is finite and the measurable function is non-negative, then you can show that the set of points where the function is taking infinite values, that must have 0 mass. So, that is what we are using, but in terms of random variables. Again, what we end up having is that the expectation of this sum, which is a random variable on its own, must be taking finite values almost surely. Now, on that set of full probability, which is giving us this almost sure finiteness, here what we conclude is that since this series is summable, then the terms in the series must go to 0 as k goes to infinity. Now, this is again happening on the set of full measure or full probability, but the limit of this ratio goes to 0, that can happen only if that the numerator is actually going to 0 here, and therefore, this is giving us the fact that the subsequence of random variables must be converging to x in this almost sure sense. So, that is what we wanted to show, and this is giving us alternative proof for the fact that convergence in probability will imply almost sure convergence, but through a subsequence. So, this is a very important identification that we are obtaining for convergence in probability, and we are going to see further applications of this later on. Now, recall the following variant of the dominated convergence theorem, which was discussed earlier in proposition 8 of week 1. So, let us recall the result that we had proved in week 1. So, we are given that a sequence of random variables converge almost surely to x, and if there exists a random variable y such that it is in LP for some p greater or equals to 1, such that modulus of x n is less equals to y, then under this hypothesis what you can show is that all these random variables x, x1, x2 and so on, all of these first of all must be in LP, and moreover the convergence holds in LP. So, from almost sure convergence to LP convergence you can go if you have this integrability bound given by this specific random variable y. Now, here we are simply using this variant of the dominated convergence theorem. Now, using the understanding that we have obtained for the convergence in probability, we are going to discuss an improved version of this result, that we can relax the assumptions, but still conclude that convergence in LP holds. So, here our earlier assumptions that we are using is that the sequence of random variables converge almost surely, and the second assumption is that these random variables have a certain integrability bound given by a random variable y. Now, let us see. So, now we have this new assumptions that we are no more looking at almost sure convergence, but we are only asking for convergence in probability. As discussed earlier, convergence almost surely implies convergence in probability. So, therefore, this is an weaker assumption that we are using here, but we will continue to use the integrability bound as was stated in the earlier formulation, that there exists a random variable y in LP for some p such that modulus of x n is dominated by y. Now, here we will claim the same conclusion that all these random variables x, x 1, x 2 and so on are again in LP, and moreover the convergence holds in LP. So, therefore, we can go from convergence in probability to convergence in LP, but provided there exists a certain integrability bound of this type, and this is the usual type of a bound that we ask for convergence in the sense of DCT, the dominated convergence theorem. All right. So, let us see the proof. So, we are given that the random variables are dominated by y for all n. In particular, this structure immediately gives us that y must also be non-negative. Now, since y is in LP, we have these interesting bounds that taking expectations on both sides, we will end up with these upper bounds, and therefore, the pth absolute moment of x n must be finite, and as a consequence we have that all these random variables x 1, x 2 and so on must be in LP for all n. But now, we want to show the same thing, similar type of a expectation bound, pth absolute moment being finite, but this is for the limit random variable. So, this is now our target, and to do this we start by looking at certain interesting inequalities. We start by fixing a arbitrary epsilon positive and look at this kind of a bound. So, first our idea is that we would like to still show an bound of this type, but with certain appropriate updates. So, let us see what we can prove. So, that is why we are looking at the situation when modulus of x exceeds y plus certain number epsilon. So, that is the event that we are looking at. Now, we are already given that y exceeds modulus of x n. So, therefore, you immediately have this inequality for modulus of x. So, therefore, from this we have that the left hand side event is contained in the right hand side event. Now, this right hand side event is further contained in another event of this form. So, here we use the triangle inequality that modulus of x is dominated by modulus of x n and modulus of x minus x n. So, therefore, as soon as modulus of x greater than modulus of x n plus epsilon, immediately you will conclude that modulus of x minus modulus of x n exceed epsilon, but now use the triangle inequality that we have stated to conclude that modulus of x minus x n must be exceeding epsilon. So, therefore, the left hand side event that we have started off with is contained in the right hand side event. Now, appeal to the monotonicity of the probability measure that we are using, and hence you have that probability of the event that modulus of x exceeds y plus epsilon, that is dominated from above by this quantity. But now, what we are having is that we assume that x n converges to x in probability, and therefore, this right hand side quantities goes to 0 as n goes to infinity, and the left hand side quantities that we have here are not depending on n. Therefore, if we take limits on both sides of this inequality, what we will get is that these probabilities must be 0, but this is true for all epsilon positive. Now, we will choose some very specific forms of epsilon. What we do is that we now look at the new event that we are interested in, which is modulus of x exceeds y. this happens possibly through this intersection, that whenever omega is such that modulus of x exceeds y, then it will happen through these union of events. So, there is a correction that will be made in the lecture notes. So, this will be union of these events of this form, meaning whenever omega is such that modulus of x of omega exceeds y of omega, that means that there exists some number which is of the form 1 by n such that modulus of x also exceeds y plus 1 over n. So, that is what we are using here. Now, therefore, the left hand side event is the union of all these type of things. But now, here note that we can use the continuity properties of the underlying probability measure to claim that the probability of this event is actually the limit of these probabilities, and for each fixed value of epsilon we have shown that these probabilities are 0, and therefore, if we choose epsilon to be 1 by n, these probabilities are still 0. Now, hence what we have concluded is that the probability of these things is actually 0. But now, what happens is that you use this fact that with 0 probability modulus of x exceeds y, and hence with full probability modulus of x must be less or equal to y. So, therefore, modulus of x is less or equal to y almost surely, and this immediately will imply that expected value of modulus of x to the power p is less equal to expected value of y to the power p, which is finite, and hence x, the limit random variable, must be in LP. So, therefore, we have ended up showing that the limit random variable now is also in LP. So, on the outset we only have assumed the bound for the individual sequence of the random variables, and for the sequence of random variables x 1, x 2, x n, we have shown first that the upper bound given by the random variable y is giving us the integrability. But now, what we are also saying is that as long as x n's converge in probability to the limit random variable x, the limit random variable x must also have this upper bound given by y, but in the almost sure framework. But that is good enough for our purpose, because we only want the finiteness of the pth absolute moment of the limit random variable, and that is following from the upper bound given by y, and therefore, the limit random variable is in the LP space. Now, we want to discuss the convergence part of it, that we want to show that x n must converge to x in LP. Now, if possible, assume that this convergence does not hold. But what does it mean by saying that this convergence does not hold? It means that there exists some epsilon positive and some subsequence x n k of the original sequence of random variables, such that these moments do not go down to 0 and they stay above epsilon. So, the moments are the pth absolute moment of x n k minus x. So, for this sequence to not converge to x in the LP spaces, this is what we will end up with, that there exists this threshold epsilon, that is a barrier for this specific type of a subsequence. Now, we will use this specific subsequence to make our argument. Given that for this specific subsequence we have convergence in probability. Now, in the first result that we have discussed in this lecture, that was theorem 1, we can extract a further subsequence of x n k, which we denote by x n k subscript L. So, that is the further subsequence that we are looking at, and that will converge almost surely to the limit random variable x. Now, let us look at this further subsequence that we have extracted. For the further subsequence also, we have these upper bounds given by y, and due to the almost sure convergence appealing to the dominated convergence theorem, we can argue that the further subsequence converges to x in LP. So, here we have just appealed to the dominated convergence theorem. In particular, the convergence in LP will tell us that the pth absolute moment through this further subsequence x n k l minus x, the pth absolute moment of that should go to 0 as L goes to infinity. So, this is for the furthest subsequence that we are using, but the furthest subsequence actually is a subsequence of the subsequence x n k. So, x n k l is a subsequence of x n k. Now, for the x n k, we had shown earlier that if the convergence in LP does not hold, then these pth moments can be dominated from below by this number epsilon. So, this is written in this statement star. Now, since this further subsequence are also in this subsequence x n k, they must also satisfy this lower bound given by epsilon as in star. So, this therefore, will contradict the fact that this furthest subsequence converges to x in LP. So, we ended up having a contradiction, hence we conclude that our original assumption must be incorrect. That is, we must have that the original sequence itself converging to x in LP. So, therefore, we have obtained improved result from earlier. So, from earlier version that we have stated through the dominated convergence theorem was that the sequence of random variables, if they converge almost surely and if they have this common bound given by LP random variable y, then you will have LP convergence for the sequence. But now we are saying we can relax the assumption from almost sure convergence to convergence in probability, but continuing with this upper bound given by a LP random variable, and we can still conclude that the sequence of random variables converge in LP to the same random variable x. So, this is a important applications coming from the equivalent formulations of convergence and probability that we have been discussing. So, in the next lecture we are going to see some interesting problems and exercises involving the content that we have covered in this week, and in the next week we are going to see some further applications and properties of these various modes of convergences. We stop here. Thank you.